So after finishing the linear algebra part of the course, we're going to start studying the mechanics part. And we're going to start by studying what the stress is, what is the stress tensor, what is the traction vector, what is the normal stress, what is the shear stress, and what are the stress-based failure criteria, and what are the different measures of stress that we can use to describe the stress inside a beam from a continuum mechanics point of view. Now, we all studied the word stress before, and in this lecture, we're going to, or in this part of the lecture, we're going to study, we're going to look at the stress, we're going to try to understand what the stress matrix is, and what the difference between stress and the force per unit area on a surface is, and we're going to study the normal stress and the shear stress on a surface, we're going to end up with, and then we're going to end up with some examples to clarify the concepts that we're going to present here. So first, we're going to start by a simple example. Just as an introduction, if I have a beam, I'm going to apply force F equal to 1 units, equally distributed on this area, and let's say the area is equal to 1 unit, and F over A is equal to 1 units of force per unit area. And let's ask the question, what is the stress at this point and what is the stress at this point? Are they different or are they the same? So it turns out that I cannot just ask you what the stress at a point is, because right here, if you're looking at this direction, well, you can say, well, I have kind of a stress that's equal to F over A. Now, if I look at it from this direction, nothing is pulling this point from above, so maybe it's 0. Now, if I look at this direction, well, I've got a component that's pulling on this point, and so I might have a stress in this direction. So basically, the concept of a stress at a point is not really described by a number. I cannot just give you a number and say this is the stress at a point. On the other hand, if I take a plane, basically, if I separate the material right here, if I separate the beam right here, I can now talk about stress on the surface, because the stress on the surface will be equal to a vector, if I call this E1, E2, and E3. Then the stress on the surface will have a component of 1 in the horizontal direction, a component of 0 in the vertical direction, and a component of 0 in the third direction. So the stress on the surface is actually a vector of forces per unit areas. Now, I could have separated the beam on a different plane. I could have separated the beam on this plane. And so the forces on these planes are also in these directions. And now the stress on this plane is equal to and let's say this angle is 45 degrees. So to find the stress on the surface that's inclined with an angle 45 degrees, in the horizontal direction, in the direction of E1, I have a total force F is equal to 1. But the area of this plane is actually equal to 1 over cosine 45 degrees. So this will be equal to 1 divided by the area, which is equal to cosine 45 degrees. In the direction of E2 and in the direction of E3, I have 0 and 0. So if you look at the stress on the vertical surface, the stress on the vertical surface is equal to 1, 0, 0, the vector 1, 0, 0. The stress on that inclined surface is actually equal to cosine 45, 0, 0. Now let's separate the beam or in a different plane. So I'm going to separate the beam horizontally. I'm going to cut it horizontally. And I'm going to look at the forces that are acting in between those two planes. So in fact, the forces here, the stress on this surface in the horizontal direction, there are actually no forces in the horizontal direction because this one counteracts the left, counteracts the right, so I've got 0. In the vertical direction there are no forces, so 0, and on the third direction there are also no forces, so 0. So it turns out that the stress on the surface depends on the orientation of the surface. And so I'm not really able to say give you a value of the stress at a point unless you tell me what the orientation of the surface that you're describing is. Because if you're describing the surface, the vertical surface, I get a certain stress vector, or as I'm going to call later, attraction vector. If I look at the surface that it's inclined with 45 degrees, I'm going to get another stress vector. If I look at the surface that's inclined horizontally, I'm going to get another vector which happens to be 0 in this case. So the stress really at a point is not really described by a number. And here is just a table to show you the stresses on different angles, or on planes inclined at different angles. Now this table is just for illustration and only applies to the beam shown. So the shown beam, I have the stress is equal to F over A, the stress on this vertical surface. If I look at a plane that's inclined to the horizontal by 45 degrees, this n1, this is the normal vector to this plane. The traction vector on this plane is going to be this vector f over a cosine 45, 0, 0. n2, if it's inclined by 30 and 60, the traction vector will have a different value. And n6, the plane, the horizontal plane, or the plane that's perpendicular to E2, n6 is equal to 0, 1, 0. The traction vector is actually equal to 0. So what we're going to show in the next little section is that we're going to describe the stress as a matrix. And what we understand is that a matrix is a linear map between the Euclidean vector spaces. So we're going to present the stress as a linear map between an area vector called n and gives me a traction vector called Tn, such that Tn is equal to sigma transpose n. So what does this mean? It means the following. Given n, in R3, where n is equal to n1, n2, n3, a vector with 3 components, and then the traction vector, which is the force or the vector of forces per unit area acting on the plane perpendicular to n. So this is n, this is the plane. The force per unit area, the traction vector T1, is going to be given as a matrix multiplication of the stress, matrix called sigma transpose, multiplied by the vector n, and Tn is equal to sigma transpose multiplied by n. So we're going to introduce, first we're going to try to understand what is Tn. Tn basically is called the traction vector. So Tn is the traction vector. If I have a beam and I separate the beam at a certain plane, and then I look at a very small area on that plane, and I say that the force per unit area, or the forces acting on this area, is a vector called delta P, and if this area of this plane is equal to delta A, then the traction vector is equal to the limit as this area goes to 0 of delta P delta A, which will be a vector Tn1, Tn2, Tn3. A vector with 3 components. So the traction vector is a vector 3 components that gives me the forces per unit area in the direction vector E1, E2, and E3 acting at this point on this plane. The next thing we're going to present is the Cauchy stress tetrahedron, or the Cauchy stress matrix. So if I have a continuum and a small, I can extract a small cube from that continuum, take it out, and look at the forces on its faces. And then I'm going to look at the face that's perpendicular to E1, face perpendicular to E1, and this is the vector, unit vector E1, the basis vector E1, and I'm going to call the force in the unit force in the direction of E1, or on the face perpendicular to E1, and in the direction 1, I'm going to call it sigma 1. So sigma 1 is the force component per unit area acting on the face perpendicular to E1, and the component itself is in the direction of E1. What about sigma 1, 2? Well, sigma 1, 2 is equal to the force component per unit area acting on the face perpendicular to E1, the first index, and the component of the force itself is in the direction of E2. So basically, if this is E1, this is E2, and this is E3, I call the force per unit area in this direction sigma acting on 1 in the direction 1. I call the force per unit area in the vertical direction sigma acting on face 1 in the direction 2. I call this sigma on face 1 acting in the direction 3. And this is how I define sigma, and then I will form a matrix called sigma made out of these components. So knowing the stresses on the vertical face and knowing the stresses on the horizontal face, what about the stresses on an inclined face? What is Tn? And it can be shown using Newton's equations of equilibrium. The sum of forces in the horizontal direction is 0, the sum of forces in the vertical direction is 0, and the sum of forces in the third direction is 0. You find that the traction vector, or the force per unit area on a general surface, is in fact equal to the sigma transpose multiplied by n. So if you want to find the stress on any surface, all you have to do is find n, find the stress matrix at a particular point, which is given by 9 numbers, and then multiply this matrix, or the transpose of this matrix, by n, and you get a vector of the forces per unit area. And so you get that the forces per unit area, Tn1, Tn2, Tn3, is equal to this matrix multiplied by n1, n2, n3, where these are the components of the perpendicular to the unit area. in fact, we can even extend our definition of the stress matrix and or augment it by the fact that the stress matrix, because of physical arguments, is actually a symmetric matrix. So because of the physical argument that the sum of moment is equal to 0 at this point, you will find that sigma 1, 2 is in fact equal to sigma 2, 1, which means that the stress matrix, this is sigma 1, 2, this is sigma 2, 1, this is sigma 1, 1, sigma 2, 2. The stress matrix is in fact a symmetric matrix, so if I put here sigma 1, 1, sigma 1, 2, and sigma 1, 3, I can actually put here sigma 1, 2, sigma 2, 2, sigma 2, 3, and sigma 1, 3, sigma 2, 3. So these diagonal components are equal. This guy is equal to this guy. This one is equal to this one. And finally, this one is equal to this. And so the stress matrix is symmetric, which means I only need to know 6 components rather than 9 components. So what does it mean that this, what does this lead to if I know that the stress matrix is a symmetric matrix? Right away, I visit symmetric matrices in the linear algebra part. To realize the following, that a symmetric matrix can be diagonalized, or a symmetric matrix has 3 real eigenvalues and 3 real orthonormal eigenvectors, and there is a coordinate system in which the matrix representation of the stress is diagonal. Okay, what does this mean? It means if I have a coordinate system here where sigma is defined as sigma 1, 1, sigma 1, 2, and it's symmetric, so sigma 1, 2 as well, sigma 2, 2, so the stress is equal to sigma 1, 1, sigma 2, 2, sigma 3, 3, and this is symmetric, and the diagonal components are not 0. There is a coordinate system Q. There is another coordinate system where here I'm going to put lambda 1, here I'm going to put lambda 2, where these are the eigenvalues of the stress. or of the matrix sigma, and in this coordinate system sigma is in fact equal to lambda 1 0 0 0 lambda 2 0 0 0 lambda 3. And how can I find q? Q is the coordinate transformation made out of p, q, and r, where p, q, and r are the eigenvectors normalized, of course, of sigma. Now we call these eigenvalues, we call lambda 1, lambda 2, lambda 3 of sigma the principal stresses. Okay, well, let's go right away into example before just to see how we can apply these concepts. So I have a plane state of stress where all these components are 0, and at a certain point I have a stress matrix made out of sigma on 1, sigma on 2, and it's symmetric, so this value is equal to sigma on 2 as well. This is equal to sigma 2 2, and because of equilibrium the other opposite side is also equal, and we want to find the principal stresses and the principal directions. So in this coordinate system described by E1 and E2, the stress is in fact equal to sigma on 1 1, sigma on 2 2, sigma on 3 is 0, all these are zeros, and then it's symmetric, so 2 and sigma to 2 is 1. Now I can ignore E3 and work in R2. And so I'm going to just use sigma, therefore sigma is equal to 1 2 2 1 in this coordinate system where E1 and E2. Now there is another coordinate system. I'm looking for that coordinate system where made out of E-1 and E-2, where sigma prime in this coordinate system is in fact equal to lambda 1 0 0 lambda 2. So how can I find this new coordinate system? I need to find the eigenvalues and eigenvectors of the matrix. I need to find the eigenvalues of and the eigenvectors of sigma. So you can do it using Mathematica as you see in a video, or we can just do it by hand. I think I made a mistake here. Yes, I apologize. This is 4. Okay. Sigma on 1 is equal to 4. Okay, well, so let's find the eigenvalues and the eigenvectors. So let's do it by hand. I need to form the matrix sigma minus lambda I. This is equal to 4 minus lambda, 2, 2, 1 minus lambda. I want this matrix to be not invertible, so I'm going to take its determinant. I'm going to make it equal to 0, 4 minus lambda, 1 minus lambda, minus 2, multiplied by 2, equal to 0. From here, you'll get that the first eigenvalue is 5, second eigenvalue is 0, and if you substitute so sigma x equal lambda 1x, what is x? So to find eigenvalue, okay, so 4, 2, 2, 1, multiplied by x1, x2 is equal to 5x1, 5x2, which is lambda x1, which means in fact negative 1, 2 and 2, negative 4 multiplied by x1, x2 is equal to 0. I basically just rewrote the first equation. 4x1 plus 2x2 is equal to 5x1, which means negative x1 plus 2x2 equals 0. So negative x1 plus 2x2 equals 0. And the second equation is 2x1 minus 4x2 equals 0. Now this matrix is not invertible, which means I won't be able to find a solution to this. So I'm going to assume a value. And if you assume x2 is 1, you'll find that x1 is equal to 2. Therefore, eigenvalue 1 will be equal to 2, 1. Normalized eigenvalue 1 will be equal to 2 divided by the norm, and the norm is equal to the square root. So norm eigenvalue 1 is equal to the square root of 4 plus 1, which is the square root of 5. So 2 divided by square root of 5, 1 divided by square root of 5. The second eigenvalue, same procedure. Second eigenvalue will be negative 1, 2. And so the normalized eigenvalue 2 will be equal to negative 1 over square root of 5. And 2 over square root of 5. Okay, so what does this mean? It means that in the original coordinate system, E1 and E2, the stress matrix has this form: 4, 2, 2, 1. If I actually choose another coordinate system made out of eigenvalue 1 and eigenvalue 2, the normalized version, which is 2 over root 5, 1 over root 5, and this one is equal to negative 1 over root 5, 2 over root 5. If I choose this coordinate system, and if I find Q that takes from this original coordinate system to this new coordinate system, I will find that the stress matrix here is actually a diagonal. Stress prime here will be equal to Q sigma Q transpose, and if you perform the calculation, you will find the stress is equal to the eigenvalues of the diagonal components are equal to the eigenvalues, and the other the off-diagonal components are equal to 0. And of course Q in this case is made out of the components of the eigenvalue 1 and the eigenvalue 2, so 2 over root 5, 1 over root 5, negative 1 over root 5, and 2 over root 5. Now the last section in this part of the lecture is the normal stress and the shear stress on an area. So the normal stress is in fact the component of the traction vector that is the orthogonal projection on n. So the orthogonal projection of Tn on the unit vector that's perpendicular to the surface, that gives me the normal stress on an area. And the shear stress is actually the remaining component. So let's remember, or let's revisit the orthogonal projection that we studied in the first, in the linear algebra part. So if I have, this is my unit vector that's perpendicular to the area, and this is Tn. This is Z bar. This is the orthogonal projection of Tn on n. So orthogonal projection of Tn on n is equal to Tn dot n in the direction of n divided by norm n squared, which happens to be equal to 1. So visit orthogonal projection in first two lectures. Now this Tn dot n, I call it sigma n, which is the normal stress on the surface. Now the shear stress is defined as the norm of the remaining component, the size of the remaining component. Now the remaining component is in fact equal to Tn minus its orthogonal projection, and the orthogonal projection is this. And this gives me the shear stress on that plane. So let's give a numerical example to show how we can do these calculations. Of course, if you've done this using Mathematica in the first few assignments, it's very simple to do it here. It's a direct application of the linear algebra part. So I have a continuum. At a point, I'm given the stress matrix of 1, negative 1, negative 1, negative 5, 0, 0, 0, 0, 4. The stress matrix has to be symmetric. If I give you a stress matrix that's not symmetric, then there's something, then it's a mistake. I need to find the normal and the shear stress components on an area. So I need an area, and that's perpendicular to the direction 1, 1, 1. I need to find the normal stress and the shear stress. To find the normal stress and the shear stress, the first step, find n, where is unit vector perpendicular to area. So n in this case is equal to 1, 1, 1, of course, divided by square root of 3, square root of 3, square root of 3. Make it clearer, 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. Where square root of 3 norm u is equal to square root of 3. So this is my normal vector. So now I have an area with a normal vector n. Then I want to find the force vector per unit area, Tn. Tn is equal to sigma transpose n. Sigma is equal to sigma transpose. This is 1, negative 1, negative 1, negative 5, 0, 0, 4, 0, 0, multiplied by n, which is 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. This will give me 1 over square root of 3, multiplied by 0, negative 6, and 4. So this is the force per unit area vector. To find the normal stress is the projection of Tn on n. I'm going to take the dot product between Tn and n. Well, Tn is 1 over square root of 3, 0, negative 6, 4. Dot n is 1 over root 3, 1, 1, 1. Take the dot product means multiply each component by the corresponding component and multiply 1 over root 3 by 1 over the root 3. So you'll get 1, 3. 1/3 multiplied by negative 6 plus 4, which is equal to negative 2 over 3. Negative means compression, which means that the vector Tn is opposite to n. Basically, if this is n, Tn is in the opposite direction, or it has a component that opposes n. So it's a compression on the surface. Now the shear stress is basically the norm of the remaining part of the force vector. So the force vector is Tn. Its normal component is sigma n in the direction of n. I'm just going to do the calculation. Tn is 1 over root 3, 0, negative 6, 4, minus sigma n is equal to negative 2 over 3, so I'm going to take plus 2 over 3. N is equal to 1 over root 3, 1 over root 3, 1 over root 3. So if you add those two vectors and you take the norm, the shear stress will be equal to 2 root 38 divided by 3 units of force per unit area. And similar here, this is also force per unit area. So let's just understand this or view this. This is n. The component in this direction is equal to negative 2 over 3. Force per area. And the component in this direction is equal to 2 root 38 over 3, which is the shear stress. Again, units of force per unit area. Okay, the next example is extremely important. The case of a hydrostatic stress. So assuming that the stress at a point inside a continuum is given by the stress matrix sigma, which is equal to P 0, 0, 0, P 0, 0, 0, P, where P is a real number. So P, any real number, 1, 2, 3, whatever, multiplied by the identity matrix. So sigma is equal to Pi, where P is an identity matrix. P is a real number and I is the identity matrix. We want to find the normal stress on any surface. And we want to find the shear stress on any surface. And we want to show that any surface n, the normal stress is P and the shear stress is 0 for any surface. Okay, well, let's assume n is equal to N1, N2, and 3. Shear stress is equal to, so the Tn is equal to sigma transpose n, and sigma is equal to pi. So pi n is equal to pn, where p is a real number and n is a vector. The normal stress sigma n is equal to Tn dot n. Pn dot n dot n is equal to p norm n squared. This is a Euclidean vector space, so this is valid. The dot product is equal to the square of the norm. N dot n is equal to norm n squared, which is equal to 1, which means that the normal stress is always equal to p. What about the shear stress? The shear stress is equal to the norm of Tn minus the normal stress in its direction, while Tn is equal to Pn. Sigma n is p, n. This is a vector Pn minus Pn. This is the zero vector. The norm of the zero vector is equal to 0. So what does this mean? It means if you go down in the ocean and you put a piece of metal, the shears, and so this piece of metal is under P, and P from all directions. If you cut any plane inside that piece of metal, if you cut any plane, the shear stress is always equal to 0, and the normal stress is always equal to P. So there are two more examples that you should look in your book or review in your book. The first example is, I have a stress matrix, a symmetric stress matrix, and we need to find a new basis set at which the stress matrix is diagonal. So I know, given E1, E2, and E3, sigma is given. I need to find the eigenvalues or eigenvectors of sigma, and I need to form Q that transforms from this coordinate system to this new coordinate system, and in this new coordinate system sigma prime should be equal to a diagonal matrix, and the diagonal components are the eigenvalues, or what we call principal stresses of sigma. One last example. We hear a lot about the case of pure. I'm sure you heard a lot in previous courses about the case of pure shear stress. Now, I just want to show you that the case of pure shear stress really depends on the coordinate system. So let's assume that I have this case, sigma on 2, where sigma on 1 is 0, sigma to 2 is 0, and everything else is 0. So sigma in this coordinate system is equal to 0, sigma on 2, Since it's a symmetric matrix, what we said applies. There is a coordinate system made out of eigenvalue 1, eigenvalue 2, eigenvalue 3, and in this case, or in this coordinate system, sigma has sigma 1, 0, 0, 0, sigma 2, 0, 0, 0, sigma 3, where these are the principal stresses and there's no shear stresses. So in this cube, there are in fact no shear stresses. So even when you say it's a pure shear stress, it really depends on the coordinate system, because if I change the coordinate system, I'm going to get sigma 1, sigma 2, and sigma 3, and I will have no shear stresses in the new coordinate system. All I have to do is find the eigenvalues and the eigenvectors, form Q, use Q to make a transformation between this coordinate system and the other coordinate system and the new coordinate system, find the stress in the new coordinate system, and lo and behold, the stress in the new coordinate system is diagonal and there are no shear stresses. So this is it for this section, and in the next section we're going to continue with stress measures and stress invariance.